So, if you've ever found yourself wondering exactly how these massive AI models manage to pull highly relevant contextual information seemingly out of thin air, well, it all comes down to what we're digging into today. Welcome to this explainer on Chapter 7 of The Developer's Guide to AI. For us working developers making the shift from traditional software architecture to an AI-native setup, it introduces a lot of new paradigms. But honestly, absolutely none of them are quite as foundational as the vector database. Today's explainer is entirely focused on vector databases in practice. We're going to go way beyond the high-level buzzwords and really break down this complex AI theory into practical, actionable mechanics that you can take and apply directly to your own development workflow. Let's get into it.
Okay, here is a quick look at our roadmap for today. First up, the data search dilemma. 2, the magic of embeddings. 3, how vector retrieval works. 4, hands-on with Chroma database. And finally, number 5, the future of search.
All right, Section 1, the data search dilemma.
As developers, pretty much all of the software we write revolves around one central thing, right? Data. We spend our entire days adding it, tweaking it, and most crucially, trying to fetch the right pieces of it back. For decades now, we've leaned heavily on relational databases and exact keyword matching. And look, traditional databases are absolutely fantastic when you have exact specifics. If you know the exact user ID or the specific product category or a precise price range, they execute those deterministic queries flawlessly every single time. But traditional databases get incredibly brittle the second you introduce the messiness of human language. I mean, think about writing an SQL query for a product catalog using a like clause. You might write something along the lines of where description like %winter jacket %. And hey, if a user searches for winter jacket, that works great. But what if the database record actually describes the item as a heavy parka or, I don't know, a cold weather fleece? Well, your traditional database just returns 0 results. We end up spending countless engineering hours trying to hack our way around this rigidity, right? We build complex synonym mapping tables, brittle tag systems, heavy full-text search configs, but it is always so fragile. This is exactly where vector databases swoop in as a highly sophisticated solution. They literally do not care about matching a specific letter's WINTER. Instead, they rely on specialized AI models to evaluate the actual semantic meaning and context behind the query. So when that system processes a search for a winter jacket, it inherently understands the broader concept of cold weather outerwear. The meaning triumphs over the exact text. It allows the system to surface that heavy parka because it knows it's contextually relevant, completely eliminating our need for that rigid keyword matching. It's a total game changer.
Moving on to Section 2, the magic of embeddings.
So to really understand how a database can actually process meaning, we have to look at the mechanism that bridges the gap between our abstract human language and cold, hard data structures. And that mechanism is the vector embedding. At the pure code level, an embedding is essentially just a massive array of floating point numbers. It might look like an array starting with 0.124, then negative 0.87, and so on, and it just keeps going for hundreds or even thousands of dimensions. You can think of embedding models, which are really just specialized neural networks, as this incredibly complex translation layer. Their whole job is to take unstructured data that humans get, like a text document, a product image, or a piece of audio, and transform it into a multidimensional spatial map. Imagine plotting data on your standard X and Y axis, but instead of just 2 dimensions, you've got, say, 1,500 dimensions. One dimension might mathematically represent a concept like warmth, another one might be formality, and another could be color. The neural network assigns specific numeric values to all of these dimensions based on whatever characteristics the data has. Because of this, these abstract human concepts are literally turned into concrete spatial coordinates. That means parka and winter jacket end up with very similar numeric arrays because their conceptual coordinates place them in the exact same neighborhood in that high-dimensional space. The machine still doesn't understand English, right? But it absolutely understands that these 2 arrays of floating point numbers are sitting right next to each other.
Let's trace the actual flow of data here. When raw human-readable data, whether that's documents, images, audio, enters your system, the very first thing it does is pass through one of these embedding models. The model transforms that raw data into a numeric vector representation, and that array of numbers is what actually gets stored in the vector database. That's your ingestion phase. But the real magic happens at query time. When a user types a search into your app, that text doesn't go straight to the database. First, the query gets passed through the exact same embedding model you used during ingestion. This generates a brand new vector array that represents what the user actually wants, their intent. The vector database then takes over and performs a mathematical similarity search. Instead of looking for matching strings of text, the database uses distance metrics to calculate proximity. Common mathematical formulas for this include things like cosine similarity, which measures the angle between two vectors to see how closely they align, or dot product, which evaluates both direction and magnitude. Basically, the database just crunches the math to find the vectors in storage that are spatially closest to the user's query vector. It fetches the nearest neighbors. The shorter the mathematical distance between those vectors, the more contextually relevant the original data is to what the user searched for.
Which brings us to Section 3, how vector retrieval works.
Now, calculating the cosine similarity between a user's query and, say, a few thousand records in a database, that is extremely fast. That's what we call a k-nearest neighbor, or KNN search, which exhaustively checks every single record. But as developers, we are building systems that need to scale, right? What happens when your database has 10 million embeddings? Or a billion? Exhaustive comparison has a linear time complexity, O of n. Comparing a query against a billion records one by one would literally bring your application to a grinding halt. So to solve this massive scaling issue, vector databases rely on approximate nearest neighbor, or ANN algorithms. ANN algorithms make a highly calculated trade-off here. They sacrifice a tiny fraction of perfect accuracy in exchange for a massive exponential boost in retrieval speed. They pull this off by using clever indexing and clustering techniques that are purpose-built for high-dimensional space. We're talking about things like hierarchical, navigable small world graphs, say that 3 times fast, or inverted file indexes. Think of these algorithms kind of like organizing a massive city. If you need to find a specific friend, an exhaustive search would mean knocking on every single door in the entire city. Nobody has time for that. ANN algorithms, instead, cluster similar data points into neighborhoods ahead of time. When a query comes in, the algorithm instantly identifies the correct neighborhood, and then it only searches the houses on that specific block. This clever shortcut lets the database skip millions of irrelevant calculations and return those nearest neighbors in just milliseconds.
All right, Section 4, hands-on with Chroma database.
You know, it is honestly incredibly refreshing that despite all the heavy machine learning math, the advanced neural networks, and the high-dimensional algorithms happening under the hood, working with these systems feels totally familiar. We don't actually need a PhD in machine learning to use this tech. We just need to understand basic data operations. If you're initializing a client for a free, open-source vector database like Chroma in your backend code, you just start by creating a collection. And a collection is conceptually identical to a table in a relational database. From there, mapping the standard developer acronym of CRUD, create, read, update, delete, directly to the Chroma API is remarkably straightforward. When you want to insert a new document, you simply call the add API. In fact, a lot of modern tools like Chroma have built-in wrapper functions that will automatically ping the embedding model for you in the background if you just pass in raw text, which is super handy. To retrieve data based on that lightning-fast semantic similarity we talked about, you just use the query API, pass in your search parameters, and specify exactly how many nearest neighbors you want back. Need to modify metadata or vectors on an existing record? Just update it by its specific ID. Or if you've got a sync job running and you aren't totally sure if a record exists yet, you can rely on the upsert API to update it if it's there, or create a brand new record if it isn't. And to wipe a record completely, you guessed it, just call delete. It is the exact same fundamental CRUD pattern developers have used for decades, just seamlessly layered right on top of highly advanced AI capabilities.
And finally, Section 5, the future of search.
So what is the ultimate takeaway from Chapter 7? Ultimately, it's that vector databases unlock an entirely new paradigm of software architecture. Because they index data in a high-dimensional space, they fundamentally understand context. By prioritizing semantic meaning over exact keyword matching, we can build vastly superior experiences for our users. Think about the architecture for AI applications that use Retrieval-Augmented Generation, or RAG. By chunking up massive amounts of proprietary company documentation and storing it in a vector database, an enterprise app can instantly retrieve the specific contextually relevant paragraphs it needs to feed into a language model. This grounds the AI's responses in factual internal data and stops it from hallucinating. Or even just consider standard e-commerce recommendation engines. Instead of relying on a user clicking a rigid category tag like shoes, the application can evaluate the semantic embedding of a user's entire browsing history to suggest products based on a highly specific style or vibe. We are rapidly moving past the era where users get frustrated by zero results found pages simply because they made a minor typo or used a slightly different descriptive word than the database administrator originally chose to write down. We are now retrieving data based on actual human intent. Take a look at the software you are building right now. What traditional search features in your apps are currently frustrating your users because they demand exact keyword matches? How many fragile synonym mapping tables or incredibly complex search indexing rules are you currently maintaining just to handle basic user queries? And more importantly, how are you going to revolutionize those features using the power of vector databases and semantic search? Definitely something to think about as you write your next line of code. Thanks so much for exploring this with me today.